Hello, and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome to all of our viewers from around the world. Thank you for joining us today. Please let us know where you are watching from. Also, welcome into listeners on the podcast version of SETI Live, available on most podcast platforms. Today, we are delving into the outer reaches of our solar system, far beyond Neptune, where astronomers have discovered something truly remarkable, a rare trans-Neptunian object that shares a synchronized orbit with Neptune itself. To help us understand this discovery, I'm thrilled to welcome Dr. Rosemary Pike, lead author of the study and expert in planetary dynamics and solar system architecture at the Center for Astrophysics Minor Planet Center, Harvard and Smithsonian. Rosemary, thank you so much for being here.
Thanks for having me.
So, let's kind of get to know you a little bit for just a second. Tell us a little bit about, that was a long title and a lot of words. Tell us a little bit about yourself, about your background, and how you came to be involved in studying the outer solar system.
So I work at the Minor Planet Center, which is hosted at the Center for Astrophysics, which is a joint from Harvard and Smithsonian in Cambridge, Massachusetts. And at the Minor Planet Center, we basically receive all the observations people take of moving objects in the solar system, and we vet them to see if they're good observations, and we do orbit fits, and we produce orbit fits and predictions. So basically where the object is going to be in time, and also make the astrometry all available for scientists to use to further study the objects. And there are sort of two main purposes that we do that for. Firstly, for just scientific research, people need to be able to find these moving objects. And so in order to do that, you need to know where it's going to be. And also because we're tracking potentially hazardous objects as well. And so we want to find possible Earth impactors and make it possible for people to get future observations and hopefully rule out possible Earth impact.
Yes, planetary defense, very important when you want to keep your civilization around for a while.
Yeah. So I've always been interested in solar system science since I did my undergraduate degree, and I worked at Gemini Observatory for a few years before doing my PhD on resonant trans-Neptunian objects. So
I love this. I love this concept of resonant trans-Neptunian objects. I really do want to explore this some more. So you're part of the Large Inclination Distant Object Survey. So, and that's what discovered this object. So how did your team design this, and what were the science goals motivated by the design?
Yeah, so I'd been working with a large group of people on the Outer Solar System Origins Survey. So I joined that survey when I was doing my PhD, and that survey found about 800 new TNOs, so trans-Neptunian objects, and it's small bodies beyond Neptune. And that was really cool, and there were a lot of really exciting things that came out of it. But I sat down with a couple of close collaborators sort of as that survey was winding down, and we said, what are the unanswered questions where that survey didn't find enough objects to address them? And in particular, we were interested in large inclination TNOs. So these are objects whose orbits are tilted a lot with respect to the plane of the solar system, so the ecliptic Earth-Sun plane.
Okay, so when she says that, so if you've got all of the planets basically orbiting in this one plane of the ecliptic, and then you've got these large inclination ones that are coming in kind of like this, some of our comets, a lot of the TNOs.
Yeah. So all of them will pass through the ecliptic plane at some point during their orbit, but their orbits are hundreds or thousands of years. So if you want to find high inclination ones, you also need to look out of the ecliptic plane. But most TNO discovery surveys look in the plane because the bulk of TNOs are in this sort of cold, dynamically cold classical belt. Right. And so you're a lot more you can only find them if you look in the ecliptic. And there's a lot of really exciting discoveries to be made there. But there are very different kinds of objects that are high inclination, and they have different kinds of orbits. And those orbits are a signature of the evolution, the formation, and then the evolution of the solar system.
I also love that, because one of the things that has really come about since the dawn of finding exoplanets and confirming them is that the solar system is much more complicated, and that the evolutionary history of it is much more dynamic than I think we were ready to acknowledge in the beginning, because we didn't have a lot of evidence for other solar systems and what other things could look like, and that planets could move, and that, you know, they didn't necessarily stay in their spot of origination. So this is really neat that we're adding this to that pile of evidence for the evolution of our own solar system.
Yeah. So in broad terms, the idea is the giant planets in the gaseous disk migrated inward, and then the gas was cleared. And then that left the planets and then a lot of sort of remnant objects, smaller things that didn't quite make it to be planets, and a lot of belts. So you have the asteroid belt and you have the Kuiper belt beyond Neptune. And then the planets started to migrate outward, and they did it by scattering planetesimals. So Neptune's slowly migrating outward as it throws planetesimals inward, and Jupiter tosses them way out into the Oort cloud, or out of the solar system to become interstellar objects for other stellar systems. And so what's left out beyond Neptune is kind of the remnants of this scattering process. So there's some objects we think probably formed there, and that's the classical belt. And then there's objects that were implanted and actually formed further, like more sunward than they're found now, and were scattered outward during this stage of planetary migration. And so by understanding the orbits of these distant objects, we can try to understand how exactly Neptune migrated during that period of migration.
Well, I want to talk about the actual object that is the subject of this discovery and the paper. I'm going to welcome in people first. We have viewers joining us from Spain, Texas, New Hampshire, Northern California, New York, Georgia, Louisiana, Missouri, elsewhere in California, and New Mexico. So thank you, everybody, for letting me know where you're watching from. That is fantastic. Oh, and someone from Romania. Awesome. Wow. Okay, so got a bit of a global audience going here. Welcome in, everybody. Okay, so this paper talks about a specific trans-Neptunian object. So tell us about the discovery itself. What did you and your team find?
Yeah, so when we do the discovery, we take a set of 3 images. So there are a few different ways to discover TNOs. And one is to look for objects, like a series of images over a couple of hours, and look for dots that move. And the other would be to take a lot of short images and then shift them at rates of motion and stack. And we took the approach of taking just a couple of images, and you're looking for little dots. And if you've ever seen the photos of the discovery of Pluto, looks a lot like that, where there's just a little, dot. And then it's not there in the next image, but it's, nearby. And so you're trying to link objects sort of across those images. So when we do the discovery, we take a discovery set at sort of the best visibility time of year. So say that's October, right? So we take it when the objects are highest in the sky in October, but we also want to observe them a few times in that year. Because if we don't, we won't be able to find them again. Because if you just get a couple of hours of arc on an object that has hundreds of years for its orbital period, it's such a small fraction of the orbit, you can't find it again. So we actually take blind precoveries and blind tracking observations before and after. So we assume that they're moving at a standard rate for the outer solar system, which is dominated by the motion of the Earth in projection. And so we sort of expand our field of view a little bit, and we take blind images a month before, 2 or 3 months before, and then a month after, and 2 or 3 months after. And it's not until sort of all of those are taken and we run it through a bunch of software to find things that are not present in other images, and then link them all together, that we start to actually know what we found in our data. So unfortunately, we don't sit there at the telescope and see an image come out and like, wow, it's Jupiter.
I don't think anybody gets to do that much anymore.
Yeah.
Unfortunately.
Yeah, so they're not resolved. They're just little spots, and we're looking for little spots that move in a predictable way.
So it's sort of like the discovery of our latest interstellar comet, right? Like everything that we've seen has been like, a trail of little dots, obviously moving much more quickly, but same kind of concept. So
Yeah.
so tell us about this object specifically. How was it first detected and what made it stand out?
Yeah, so it was first found in 2020 in the discovery data that we took. So that's the first data that we found it in. And in the first year, you basically get a good measure of the distance of the object. And so we could tell the distance was relatively reasonable, but it looked like we might be looking at a large semi-major axis object. So that has very high uncertainty in the first year. So what that means is that the average distance it'll be from the sun over the whole period of its orbit is quite large. But its current distance was not particularly large because it was close to its closest approach to the sun.
Okay.
So that's fairly typical for these large semi-major axis objects because the closer you are to the sun, the more light you reflect back to the Earth and the easier you are to see.
Sure.
So it's not until year 2 when we start to get basically linking up additional tracking that you can see, yes, it definitely is a very distant object. And at that point, we just knew that it had a very, very large semi-major axis distance from the sun. And it wasn't until we got about a third year of tracking that we realized this object was in the 10-to-1 resonance with Neptune.
Yeah, so let's talk about that. You say in the paper, and as you just mentioned, that it has a 10-to-1 orbital resonance. So for those who are not familiar with the term, what does that mean? What is an orbital resonance, and what does 10-to-1 mean specifically?
Yeah, so the resonance basically means there's an integer ratio of the orbital periods between the object and Neptune. So Pluto is in the 3-to-2 resonance. What that means is every time Neptune goes around 3 times, Pluto goes around exactly twice. And the reason that's important, especially for an object like Pluto, is Pluto actually crosses Neptune's orbit.
Mm-hmm.
And you would think that wouldn't be stable, right? Because Neptune could scatter it out. And in fact, if Pluto and Neptune, if Pluto crossed Neptune's orbit when Neptune was nearby, it would be affected by Neptune. But because it's in this resonant configuration, it always crosses through Neptune's orbit when Neptune is far away from that part of its orbit. So Neptune is, say, on the other side of the sun, Pluto crosses through the orbit, and it's fine. It's phase protected from close encounters with the planet. And these resonances basically are islands of increased stability. So objects can be in them longer. And so it preserves objects in these types of orbits like Pluto. And so when you're talking about the 10-to-1, that means Neptune does 10 orbits for every single orbit that this object does. And it's really interesting to see that even that far out, Neptune is still important enough that, it can hold it in this resonance.
That is actually kind of amazing because Neptune's orbit is not short. So what are the timescales that we're talking about here? I threw a question at her that I didn't put in my email. I'm so sorry.
Yeah. I would think about 800 years is my best guess for the object, I think, offhand.
Wow.
But T squared is A cubed, so the semi-major axis is 140. So viewers at home can do the math.
Or you can look up Neptune's orbit and multiply it by 10.
Multiply by 10.
That always works too. So how do you determine this resonance from the available data? Again, these are massive timescales, even on a solar system base. Like, no, they're not. It's not light years and it's not millions of years, but still longer than we've observed astronomical objects, really. So how do you determine this?
Yeah, so what we do is we look at how we expect the object to behave over time. So we measure where the object is and we compute what its orbit is. And then we take the orbit and the giant planets and we use what we call an n-body integrator. And basically it's like calculating gravity. So it calculates the gravity of everything and it moves everything a tiny step forward in time. And then it recalculates and moves everything again. Because if you remember, you can't solve Kepler's, the Keplerian motion of more than 2 bodies unless there are some restrictions. And here, of course, we have 4 giant planets in the sun that are all very important. So we look at the object forward in time. And when we do that, we can see basically periodic behaviors in its semi-major axis, its distance from Neptune, and the angular distance that the object is away from Neptune over time. And when it meets certain criteria in these, we determined that it is definitely in resonance with Neptune. So the complication comes in that when we measure where the object is, there's an uncertainty to that, right? So we measure a little photo and we say the stars are here. I have these stars in the Gaia catalog, right? And so these stars are here, so this object must be here. But each of those measurements has an uncertainty in it. So then you have a series of measurements with uncertainty. And in order to capture that uncertainty, we use what we call clones. And so we make hundreds of objects, of orbits that are all consistent with our measurement of where the object is. So they vary a little bit in their sort of average distance and how non-round, how non-circular their orbit is, and how inclined it is off the plane, how tilted.
So a lot of what you do, I mean, this isn't to say that obviously, you know, Pluto was discovered before we had massive computers, but obviously massive computing power and that ability has really helped this particular area of science, correct?
Definitely, yeah. So Pluto was discovered by looking at plates, and you can do it by putting, you know, a different color sheet, and you have a red and a blue one, and you stack them, and you see when things are, you know, sort of cancel out and when they're the same, or you can basically blink them manually. And so we've removed a lot of that. Our searching is all done by computer, and it's not until you're like vetting candidates that the human eye is even required. And a lot of people are working on removing that human verification for the most part as well. And for our stuff, anything that is bright and not within like a magnitude of our detection limit, you really don't need human verification. The pipelines are good enough to find the moving objects. And then, of course, we use a lot of computation power when we're integrating the objects to see what their future behavior is as well.
Right. Okay. I want to welcome in a few more locations because we did get some more. Let's see. So more from California, but also, and this is where this gets kind of exciting, everybody, we have Brazil, Sweden, Mexico, and Germany, and Guadeloupe. So, wow. Oh my gosh. We're definitely getting very global here. All right. So, Rosemary, what is this, because this object have been in this position since the solar system formed? You were talking about how resonance provides stability. So, you know, for me, I study Jupiter moons, Jovian moons. So, you know, there's a lot of resonance in the Jovian system. How does that work here this far out? Is this a stable object? Can we predict it for a while?
Yeah, so there are a few things we look at. Firstly, we want to know if it's stable. Could it have formed there? We don't think it would have formed here. It's a very high energy orbit, so it's very non-round. It's off the plane. But one question we want to ask is, when the giant planets migrated, could they have stuck it there and it's been there ever since? So about 4 billion years ago. And so the short answer is no, it's not billion-year stable. So when we made all these clones of the orbit, we asked, you know, how long does it take for each of them to leave? And basically, more than half of them leave the resonance within 1 billion years. And that means that, you know, it's stable on million-year timescales. It's not stable on billion-year timescales.
Okay.
So it's part of this population of objects that we call scattering sticking. And so there's lots and lots of objects that were probably scattered out, you know, as part of this scattering process billions of years ago, and they all hop around. So they scatter off Neptune a bit, and then they stick in a resonance for a while, and then they scatter a bit, and then they stick in a different resonance. But it's really interesting to see this happening all the way out at 140 AU.
That is really amazing. What does this tell us about the evolution of our outer solar system? Or, I mean, does it tell us anything about the evolution of our inner solar system? Does it? Yeah. Talk a little bit about how planetary migration, how this might give us some evidence for that too. Like what is this? What does this look like in the big picture for our solar system?
Yeah. So I think one of the important things we need to think about is sort of the extension of mass as it goes outward. It definitely, there's massive bodies going out sort of farther than we naively anticipated, although you do see stuff going out pretty far when people run migration simulations. And so there are a lot of scientists doing really excellent work where they put the planets down and they put a disk down and they try to migrate them a bunch of different ways. And you see, does this one trap a lot of objects in resonance, or does it clear some of the resonances because of some of the more complicated interactions with, say Uranus can matter where you put Uranus as well as Neptune. And the speed and graininess with which you move the planets also matters. So you can imagine the planets Neptune could have migrated out pretty fast because it scattered a lot of things really quickly, or it could have migrated a little more slowly. If it scatters a whole bunch of small objects, it'll cause a different signature than if it scatters thousands and thousands of Plutos. And so you can see a lot of these signatures in the outer solar system. Because this object probably wasn't scattered in that large event, it's not a huge constraint. Basically, if we found a whole lot more of them, a lot more than we'd expect in the 10-to-1, that might indicate there was some process that preferentially populated really far out in sort of that region. But with one detection, it's sort of consistent with our expectations in general, based on the size of sort of known objects in the outer solar system in general, like other resonant populations.
So that kind of leads me to the next question I have is, are there other objects that share this kind of relationship with Neptune? Is this truly one of a kind, or do you have other known 10-to-1 resonances? Or, we know Pluto's in a resonance, but what other objects are we talking about here?
So this is the only object that is securely classified in the 10-to-1. So what we mean by that is that sort of all of those resonant clones show some 10-to-1 resonant behavior. And so it can be hard at these really large distances to get a long enough arc to be able to say that conclusively. And we were lucky with this object. There was some archival data we were able to get that extended our arc as well. So there is another object in the possibly in the 10-to-1 resonance, but it's not conclusively determined. So they still say some of their clones are not resonant, and so they had it as an insecure object. But the 10-to-1 is the farthest resonance, the largest semi-major axis for which there is a secure resonant object classified.
So, okay, we're starting to get some questions in from the audience. So thank you, everybody. I'm going to get to those in just a second. And you guys are asking things that I want to ask too. So, all right. What more do we need to find these rare objects? So like what do you need to confirm this one that you're looking at, or any more that you might find?
Yeah, so we have a pretty good arc on this object. It would be great to find more N-to-1 objects in general. So that would be any of these 9-to-1, 8-to-1. We in the survey, the LIDO survey, we did also have a 7-to-1 and a 5-to-1. And it would be great to find more. And like I said, kind of way back at the survey design, these are preferentially off-ecliptic. So off-ecliptic surveys are going to be a lot better at finding objects like these. And so getting more discoveries is what we need to do, say, a population estimate. How large is this resonance compared to some of the other nearby resonances? Okay.
All right, so let's look at some of these audience questions. First off, once again, Thomas Hill, thank you for your 1999 super sticker. Much appreciated. All right, let's see. Okay, this is one of the things I wanted to kind of ask you about, and I know we talked about it a little bit in our emails, but what does this say anything about Planet 9? Does this help us find Planet 9? Are you looking, what is the relation here?
Yeah, so this object in particular doesn't really provide a lot of constraints on whether or not there's likely to be additional masses in the solar system. So because it's in our known current solar system architecture, it's stable for millions of years and not billions of years. If a Planet 9 made it unstable, for example, that wouldn't mean that we're unlikely to find it in this configuration, because we already think it's probably not giga-year stable.
Right.
So for this object in particular, there's not really any any predictions we can make about Planet 9. For the LIDO survey in general, we found 141 objects, and these are all mid to high inclination. And one of the things that we are looking at is what is the inclination distribution of these objects? So how high is the inclination? And getting a good measure of the distribution of how inclined objects are in the Kuiper Belt is a good constraint on Planet 9. So for example, if there is an additional planet and it is at large, it is itself inclined, it will excite the Kuiper Belt to be more inclined. And there's not a lot of evidence for that in the current Kuiper Belt, but getting a better measure of especially the high inclination portion of it will help us say, for example, it couldn't, if there's an additional mass, it couldn't have an inclination higher than some amount. But the analysis is ongoing right now.
Okay. So sorry, everybody.
About the inclination distribution. So sorry.
Sorry, everybody. No news on Planet 9 from this. I wish. But you did mention, and I think this is a thing to clarify. We talk about trans-Neptunian objects, but we also talk about the Kuiper Belt. So what is there a difference between the two scientifically, or is it just another one of those astronomers like to put things in boxes and the boxes keep moving?
Yeah, it's the Kuiper Belt was sort of the prediction of there being another belt beyond Neptune. And there is a feature that is very much a belt, right? So that what we call the cold classical belt. And that is often referred to as the Kuiper Belt. And sometimes people use that term a little more broadly for all of these different things. I typically use trans-Neptunian objects because I feel better encompasses, say, things like centaurs, which are scattering inward from the Kuiper Belt. They're not yet comets. So basically the step between a Kuiper Belt object and a comet is a centaur. And then also the more distant things, because this object you wouldn't really think of as being in the belt. It's very, the belt sort of ends around 47 AU. And this is at 140 AU. So we're another 100 AU past sort of the edge of what we see as the Kuiper Belt, which is why I usually use trans-Neptunian objects.
I'm just kind of
they
curious.
are often used interchangeably.
And I mean, if you look at Pluto is considered a Kuiper Belt object. It is also, in all technicality, a trans-Neptunian object because it does cross Neptune's orbit. So this is one of those, it can be both and it can be either.
Yes.
Okay.
Yeah, Pluto, I would definitely say people use both.
Okay. Then what we were talking a little bit about things that would help us find more of these. Are you excited about the Vera Rubin Observatory and it's searching? What do you expect to get from that as well?
Yeah, definitely. Vera Rubin will hopefully completely change the game for these off the ecliptic objects. So there is a portion of the Vera Rubin survey targeting the ecliptic, and that's going to be great for finding lots and lots of TNOs and lots of asteroids and other things like that. But also they're going to cover the whole sky, and so they're going to be a lot more sensitive to these off ecliptic objects like this, and we hopefully will be able to find a lot more similar objects, and we'll be able to do some good population studies and figure out how many are in these different resonances.
That would be really interesting. I mean, I feel like just in the time that I've been a planetary scientist, we've gone, even the asteroid belt has become much more fully populated and on at a smaller scale. So smaller and smaller asteroids, we're getting a bigger and bigger collection of them. And Vera Rubin has already proved that it's going to add to that total as well. So I'm really excited to see how far out we can add to the population of, say, the Kuiper Belt and these trans-Neptunian objects. I'm going to ask you this question. You can feel free to say not in my realm of work here, but I'm curious myself. Is there any measurable gravitational interaction between the Kuiper Belt and the Oort cloud? Now, I'm going to say probably not. That's the Oort cloud is much further out than I think people realize. Yeah.
So the Oort cloud is a few thousand AU. So so for this object, it's at least 10 times farther away. Things from the Oort cloud could pass through the Kuiper belt, in which case it would be possible for those objects to interact, right? But it's largely empty space. It's not like in Star Trek where they go through the asteroid belt, and there's a chance of being hit. So it's mostly empty space. And yeah, there's not really any interaction between the Kuiper belt and the Oort cloud.
Yeah, I think it always surprises people that space is mostly empty. That yeah, if you want to hide in an asteroid belt, you're going to have a while to look for another asteroid.
Yeah. Yeah, if you think the New Horizons spacecraft is flying through the Kuiper belt, and a large part of the time it's there, there's nothing it can observe. There's nothing close enough for it to see.
Right.
So that there are a couple of things that they're trying to get, but mostly it's flying through empty space.
I mean, let us all remember that both Voyager spacecraft made it to the edge of the solar system without running into anything and are just continuing on their way. So
yeah.
It is very, very empty out there. Well, Rosemary, thank you so much for joining us. We've reached our half an hour, and this is incredible work. It's really interesting and exciting. I love trans-Neptunian objects. I got interested in them by a friend of mine, so that is really cool to actually get to talk about them. What is my last question for you? Is what is next for you? So this paper's done. Well, what are you working on now, and what's the direction you're heading in for your research at the moment?
Yeah, so I guess there's a few things. This object, in addition to being in the 10-to-1, is actually doing some very weird resonant behaviors that we hadn't seen previously. So there's basically a theory paper that we're working on to better understand the resonant dynamics in more detail. We're also looking at, the other 140 objects in LIDO. There are a couple of big populations. We have a bunch of objects in the 3-to-2 resonance with Pluto, which was one of the things we're really hoping to find a lot of. And we have some in the 5-to-2 resonance as well, and some of what we call mixed mode resonators, which I won't get into in depth here, but are very weird in that they're showing a sort of different resonant behavior. So we're looking at all those, and then of course also getting involved in a new discovery survey, which is called CLASSY. So it's the Classical and Large A Solar System Survey, and that's being run on SafeHT right now, and we're using shift and stack to try to find objects. So you want to go, in order to provide supplemental results to Rubin, as opposed to things that will be scooped by Rubin before they're published, you need to choose basically depth over area. And so you can go to much, much smaller sizes and better understand the small objects, where Vera Rubin is going to discover a lot of objects, but they won't go as small as, say, this particular object, the 10-to-1 in LIDO.
That's one of the things when I talked to the director of the LSST Discovery Alliance, and they have their Skyviewer app. And as she pointed out, you can look at that and you can, yes, Vera Rubin is imaging all of these things all of the time, but you may be the first person that looked at a specific object and learned more about it. So yes, they add to the catalog, but the catalog doesn't necessarily mean we know anything beyond there's a thing.
Yeah, the catalog is the starting point for understanding what it all means.
That's really exciting. And is there a place people can follow you to learn more about your work? Or have you joined the crowds of people who are not doing social media anymore?
Yeah, I don't really do much social media, but when there's exciting stuff, we try to put out a press release.
Well, then we will do what we always do and keep an eye out for those. And again, thank you so much for joining us here today and sharing your incredible work. Thank you to everybody for watching, for tuning in. Don't forget to do all the things like subscribe, hit the notification bell on YouTube so you don't miss these live streams. The next few are going to be at different times. We have a citizen science one coming up to talk about the latest results with Unistellar. And we're also going to talk about some wildlife things. And And yeah, so there's a lot of things coming up. And as always, the SETI Institute is a 501c3 nonprofit. Your subs, your bits, your super chats, your stars, your stickers, all of these things are so helpful in keeping this program running and helping me bring on incredible guests like Dr. Pike. And so if you enjoyed the conversation and you have an extra few dollars to give, please go to our website, SETI.org, and hit that donate or give now button. And then make sure that you like this video, share it with your fellow space nerds, and again, subscribe for more space science interviews. Stay tuned, everybody, and keep looking up.